Welcome to the Picture Language Seminar. It's March 22, 2022, and we're very happy today to have Robert Huang. Robert's a graduate student at Caltech, but already as a student has made remarkable insights into machine learning, classical machine learning, and he's going to tell us about that today, about provably efficient machine learning for quantum antibody problems. So Robert, share your screen.
Yep, could everyone see?
Yes.
Okay, then I'll go ahead and start. My name is Robert, and today I'll be talking about provably efficient machine learning for quantum many-body problems. This is a joint work with Richard Kuhn, Giacomo Torlai, Victor Albert, and John Presco. So recently, machine learning has received a lot of attention in the quantum community. In particular, one of the goals in applying classical ML for quantum physics and chemistry is to be able to solve challenging quantum many-body problems using machine learning and hopefully yield solutions better than traditional classical algorithms. However, despite the interest, many fundamental questions remain to be answered. In particular, in this talk, I will focus on the following question. In particular, we would like to understand how can machine learning algorithms be more useful than non-machine learning algorithms in solving physically relevant problems. So today's talk, I will provide some concrete answer toward answering this question. And the talk will be separated into the following three parts. The first part, I would talk about a brief review on this classical shadow formalism. And in the following two parts, I would talk about training machines to predict ground states and training machines to classify quantum phases of matter. I would focus on both the mathematical theory as well as present some numerical experiments. So now let's dive into the first part of the talk. In classical shadow formalism, we are trying to answer an even simpler question. In particular, how can classical machines effectively see quantum many-body systems? Here, what we mean by seeing is the ability to convert the quantum system to a classical form, so some efficient classical representation that accurately captures many properties of the original quantum system. In this paper, predicting many properties of a quantum system from very few measurements, published 2 years ago at Nature Physics, we present the following procedure in order to answer this question. The procedure is quite simple. It consists of two phases. The first phase is what we call a data acquisition phase. So in this phase, we would have a quantum system, the unknown quantum system. What we're going to do is we're going to apply a random unitary to this quantum system, followed by a standard basis measurement. So we do that for a few repetitions, and one can understand this phase as the following. So think of the quantum system as a very high-dimensional object. In the figure here, we're just showing a 3-dimensional object. Performing random unitary followed by measurement can be thought of as looking at this very high-dimensional object from a random angle. So for example, if we select a unitary U1, we're going to look at this quantum system from this random unitary angle. And by performing this measurement, we're effectively projecting this high-dimensional quantum object into a low-dimensional classical description. By doing several rounds of these repetitions, we can get this like this shadowy picture of this high-dimensional object, which allow us to understand what kind of quantum system is this. So basically, the procedure is utilizing this intuition, and that's why it has the name called classical shadow, because we are basically casting classical shadow of a high-dimensional quantum object. So now after, yeah.
I also got the impression that the quantum system is effectively infinite dimensional, but you're saying that it is just finite dimensional, even if it is very high?
Yeah, I mean, quantum systems, it depends. So if you look at atomic systems with like discretized, so like for example, if you only look at two, like the say in the Rydberg atom system, you look at ground state and the Rydberg state, and that would just be like 2. And then if you have multiple atoms, then you will have 2 to the n space. So quantum systems typically live in this like large dimensional space, like exponentially large dimensional space. But if you look at continuous systems, then it is infinite dimensional. But here we're focusing on a finite, like a, how to say, like for example, a qubit systems. If you look at qubit systems or fermionic systems, you look at second quantization, then you have like the occupation number, and that will become finite if you do truncation of this infinite dimensional space. Like for example, if you look at the box, then it would also be, yeah. So it's finite dimension, but it's an exponentially large dimension. So it's a very high dimensional object. On the other hand, the classical description, and then it's actually it's a vector in this infinite dimensional space. On the other hand, the classical description is just some 0, 1 bits. There is still an exponential number of configuration for the classical side, but as we all know, quantum systems has much higher complexity than classical representation. So now after constructing this classical representation, we will have a prediction phase. Basically, in this paper, we propose an algorithm that allows us to predict properties of this unknown quantum system by looking only at this classical representation. Furthermore, in the paper, we proved the following theorem. We showed that the previous procedure based on random measurement followed by a prediction phase guarantees the following. Suppose we are given 3 hyperparameters, which will be made clear later. The procedure can learn a classical representation of an arbitrary unknown quantum state rho by performing only b log m over epsilon squared measurements, such that subsequently, given any observable O1 to OM, so now you can see that this m basically determines how many observables one wants to predict, with a norm bounded by capital B. This procedure can use the classical representation learned from step 1 to predict the expectation value of all of these m different observables up to epsilon error. So basically, these 3 hyperparameters correspond to the norm of the observable, the number of observables, and how efficient we can predict all of them. And furthermore, you can see that in the first step, the number of measurements required, it's only b log m over epsilon squared. So now, for example, if one wants to predict 10 to the 6 different observable with a norm bounded by 1, naively, in the experiments, what we need to do is we need to perform 10 to the 6 over epsilon squared measurements, meaning that we need to perform these measurements in order to, like if we just measure each observable individually, then this is the number of measurements one need to make in order to estimate all of these expectation value. However, this theorem shows that we actually only need 6 log 10 over epsilon squared measurements, which is a huge reduction over 10 to the 6 over epsilon squared measurements. And furthermore, the observables that one wants to predict can be chosen after the measurements. So in a sense, this representation that's learned from the experiment is the form of a classical representation for this arbitrary quantum state. So in this talk, we will in particular utilize classical shadow formalism based on randomized Pauli measurements. So we're going to prove almost most of our theorems under this randomized measurements. However, it's not hard to imagine that by changing to a different measurement schemes, for example, a measurement schemes that's more friendly to experimental systems, one could also adapt the theorem that's established in this work to accommodate for that. In particular, in the randomized Pauli measurement, we consider the following. One randomized Pauli measurement corresponds to the following. Basically, for every qubit, we measure them in a random XYZ basis. So from this picture, what we're going to do is we're going to perform a random evolution that's equivalent to a tensor product of single qubit unitary, in particular, single qubit Clifford unitary. So we applied that tensor product of single qubit Clifford unitary followed by a computational basis measurement. And that could be shown to be equivalent to measuring every qubit in a random XYZ basis. Now, after performing T randomized Pauli measurements on an n-qubit system, what we'll get is this array, this STI. It's a 6-outcome array. Basically, one can think of it as follows. Suppose we look at the teeth randomized Pauli measurement. Then when we measure every qubit, we'll get a string of n outcomes, and that's indexed by this small I. The small I goes from 1 to n, where n is the number of qubits. In particular, for each of them, it will either be 0 state, a 1 state, a plus state, a minus state, a y plus, or a y minus. So basically one of these following 6 outcomes. What we're going to do here is we're going to construct a 2x2 complex matrix known as sigma ti. That's given by this formula shown here. And in order to construct this classical shadow formalism, what we're going to do is we're going to tensor product sigma t1 to sigma tn. And then we are going to average over these capital T different randomized measurements. So that creates this representation sigma t of rho. So sigma t of rho can be thought of as a 2 to the n by 2 to the n random matrix. And it's constructed such that its expectation value would be equal to this unknown state rho. And furthermore, the nicest part about this representation is that it takes very few classical bits to represent. In particular, it's not hard to see due to this tensor decomposition, it only takes order small n times capital T classical bits to represent this exponentially large matrix. So here, one should think of this rho as this 2 to the n by 2 to the n complex matrix to represent an n-qubit system. And this sigma t of rho is this particular representation that's as big as rho, but requires much, much fewer number of classical bits to represent. In particular, this capital T corresponds to the speed log m over epsilon squared, which is a pretty small number compared to, say, 2 to the n. So this is a basic technology that we're going to utilize for proving the further theorems in these other applications corresponding to training machines to predict ground state and classifying quantum phases of matter. So for the second part, we're going to focus on training machines to predict ground state. And here the task is very standard. We're given some parameters x, which is a high dimensional vector that describes an n-qubit Hamiltonian h of x. The goal of the machine is to predict a classical representation of the ground state for this Hamiltonian h of x. Here one should think of this x, say, as an m-dimensional vector. We normalize them, so it's all between -1 and 1. And each of these different entries corresponds to some description that specifies the Hamiltonian. For example, some of the entry could describe the laser intensity, some of the dimension describes the few-body interaction, some of them describe magnetic fields, etc. So the goal of the task is that given some x, the classical machines want to predict this classical representation of the ground state such that utilizing this classical representation, one could predict different properties about the ground state of the Hamiltonian. In particular, for the machine learning algorithm that we're going to propose, the mapping from x to the Hamiltonian h of x can actually be unknown. So now for people that have worked a little bit on this problem, it's not hard to see that this is actually a very hard problem in general. In particular, suppose we consider a special case. That is, we're given some smooth class of n-qubit 2-dimensional Hamiltonians. So here, 1D is just you have a chain of spins, a 2D and it's some 2-dimensional lattice. Say with a spectral gap of 1, that is, the ground state and the first excited state has a gap, like an eigenvalue, that's energy eigenvalue that's gapped by 1. And the goal of the machine is to predict one body observable in the ground state. And so furthermore, let's say we only care about the average prediction error. That is, we don't really care about predicting all x. We only care about, on average, the prediction for some randomly sampled x from this high dimensional space. We get good prediction error. One could show that even under these two conditions, in proposition 1 of our paper, we proved that assuming NP-complete problems cannot be solved in randomized polynomial time, then there's no randomized classical algorithm that can achieve an average prediction error of 1/4 within time polynomial in small n. Small n is the number of parameters in this vector x, and small n, which corresponds to number of qubits in the system that we care about. So basically, it shows that this is very hard. If we make this assumption that NP-complete problems cannot be solved in randomized polynomial time, then there's no polynomial classical algorithm that can achieve a good prediction error. And here, what we're going to look at is the following question. For this very challenging problem, can classical machine learning algorithms do something useful? For example, can they even solve these problems in polynomial time, which might just be a wishful thinking. Here we're going to focus on classical machine learning algorithm that's of the following form. So basically, there would be some training data. The training data consists of capital N different examples, and each example shows the following. Given some parameter that describes a physical Hamiltonian, we have the corresponding classical representation of the ground state. So this could be constructed as follows. Suppose we synthesize some ground state in the lab, and then we perform some measurements on it to construct this classical representation. Here, for the theoretical analysis, we're going to focus on classical shadow representation, which is an efficient representation that holds for any quantum state. But in practice, one could consider some more restricted format of classical representation. So now, after learning from this training data, the classical machine learning algorithm will be given a new parameter that describes a new Hamiltonian that have never been constructed in the lab. And the goal of the machine learning algorithm is to be able to predict a classical representation for the ground state corresponding to that new Hamiltonian. So now, after talking about the task, we would like to consider a class of machine learning algorithm that can be used to address this problem. In particular, given the training data that's shown on the right, we would like to train a machine learning model that takes in some m-dimensional vector x and outputs an efficient representation for an exponentially large matrix, which we call sigma hat of x. Despite the exponential scaling, we require that the machine learning model to be trained within time that's polynomial in both small n and small n. So for example, we can consider training a neural network that's illustrated below, where it has infinitely many neurons in the hidden layers and exponentially many neurons in the output layer. Despite all these infinity and exponentially large scaling, we can actually train this bizarrely large model in time that's polynomial in both small n and small m. In particular, based on neural network theory, one could show that the neural network after training actually has a closed analytical form. So what we mean by that is the following. Suppose we consider a loss function that's given by this. The sigma t rho of xl, that's the training data. Sigma hat w of xl, that's the output from a neural network. So this w just means the weight inside these connection between the neurons. Suppose we have this difference between sigma hat w and sigma t, and the goal of the neural network is we want to train it such that this difference is as small as possible. So one could think of it as just we're trying to fit the training data. That is, for each examples in the training data, the neural network has to match up with the output. So one could show that by doing gradient descent in these infinitely wide neural network, the resulting trained neural network actually can be written as a form that's shown here. So basically, there's this function, kappa nn, that's some learned function, which can be obtained efficiently on a classical computer. And the sigma t rho of xl corresponds to the classical representation for inside the training data. So we call that the training data is given by this form shown here. So not only does neural network admit this kind of representation, actually many machine learning models can be shown to have this pretty much the same analytical form as the global minimum after performing training on the training set. Here, this kappa is a learned function, and the sigma t is this output in the training data. So basically, one could think of sigma hat of x as a learned function that shows how one can extrapolate the known examples to entire space. So suppose that we have a training data consists of these 4 points, x1, x2, x3, and x4. Say we're given a new point x, we wanted to predict the ground state for this point. What happens here is that basically for each of these points, we have some classical representation for the ground state. So written as sigma t. So recall that rho of x is the ground state, and sigma t rho of x just means the classical representation for the ground state. And basically what we're doing here is we are going to compute this nonlinear function kappa between x, x1, x, and x2, and so on. This is a highly nonlinear function in x. And what happens is that we're going to utilize that function to perform extrapolation of these matrices. So basically, we're going to combine all of them to produce a prediction for x. And this actually holds when you train like kernel methods or you train infinite width neural network, etc. So now one could look at the prediction of the ML model. So despite this sigma hat of x being an exponentially large matrix, it's 2 to the n by 2 to the n complex matrix, it can actually be stored very efficiently on a classical computer. Basically, because each of these, if one utilizes classical shadow representation, or if one utilizes some other representation, for example, if you have matrix product state representation, etc., then the sigma t of rho of xl, recall that it only, say in the classical shadow regime, it only requires a polynomial number of bits. So here, the machine learning model's prediction also only needs a very small amount of classical bits, as long as the size of the training data is not too large. So now after describing the proposed methods, we would like to see what can we prove about this classical machine learning algorithm. So recall from proposition 1, we have the following statement, that for two-dimensional Hamiltonians with spectral gap 1, if the goal is to predict one body observable to an average prediction error of 1/4, it's not possible if you utilize a classical polynomial time algorithm. However, in the paper, we proved the following theorem. We showed that with a polynomial number of training data and one randomized measurement on each of the quantum state, the machine learning model after training can achieve an average prediction error of epsilon, where epsilon could be an arbitrary small constant. Furthermore, the training and prediction time are polynomial in small m and linear in small n. Furthermore, this classical machine learning algorithm trained with data can apply to settings where, for example, in any constant dimension, not just for 2-dimension, any constant spectral gap, predicting any few body observable, and as we have said, it can achieve a prediction error of arbitrary small epsilon, as long as it's a constant. For example, it could achieve a prediction error of 1/10, which cannot be achieved by a classical algorithm. So now in order to establish the theorem, there are a few key steps. The first is we are going to utilize spectral flow and Lie-Robinson bound to show that the ground state actually varies smoothly when this high dimensional vector x changes. So this is not it's some definition of smoothness. And then after using this guarantee, we can perform learning theoretic analysis to bound the prediction error. In particular here, that will be a combination of statistical analysis for the machine learning model, as well as the realization. In particular, inside the statistical analysis, we utilize the fact that the number of lattice points in an m-dimensional sphere with a constant radius is only scales polynomially rather than exponentially in m. And this geometric picture actually determines the number of training data that's required in order for the machine learning model to make good prediction. So now, basically, you can see that by combining proposition 1, showing that no polynomial algorithm exists, and theorem 1, showing that the proposed classical machine learning algorithm can make good prediction, it basically says that classical polynomial time machine learning algorithm trained with data can predict ground states better than any polynomial time classical randomized algorithm in the worst case in general. So one might be puzzled by this because one might ask upon question on classical machine learning algorithm, just a type of classical algorithm. Why are they more powerful than these non-machine learning traditional classical algorithms? And the answer to that is that in order for a classical machine learning algorithm to work, all it has to do is to generalize from training data. So it's built on the assumption that a training data has already been constructed, and all it has to do is to learn from the training data and make good prediction about a new input. And that could be much easier than computing everything from scratch. So for example, getting this training data could be very challenging. For a classical algorithm, it has to, if it wanted to go through this route, that is, go through the route of using classical ML, it has to first generate the training data and then train the ML model to make prediction. And that's could be much harder than classical ML algorithm because it could just learn from what it already knows. So this is an illustration of the fact that data contains computational power that can enhance loads that learn from it. So now, after talking about the theory, we would like to see how well classical machine learning algorithms perform in actual physical systems. In the first example, we are going to look at one-dimensional Rydberg Hamiltonian array. So here we consider a training data size of 20, very small, and then 500 randomized measurements for constructing the classical shadow representation. And we are going to pick one of the best machine learning algorithms chosen from Gaussian kernel methods, infinite width neural network, and L2 Dirichlet kernel. In figure A, we show the Hamiltonian for the Rydberg atom system. We put them on this one-dimensional chain, and it's basically living on either the ground state or the Rydberg state. Figure B shows the phase diagram when one tunes the Hamiltonian. So there's actually 3 phases in the regime of how we, in the parameter regime. There's this disorder phase, a Z2 order phase, and a Z3 order phase. Figure C shows the prediction of the classical ML model. Basically, the black markers shows the prediction for these 3 points, and it's trained on these gray circle. We also compare it with exact values computed from DMRG, and it's shown as the solid lines. And one could see that by using classical machine learning model, it actually, without any knowledge about quantum physics, it can produce similar results as the values from DMRG. On the other hand, if one uses a more naive strategy, for example, this nearest training data methods, that is, in order to predict these points, you just pick the closest point in the training data to make prediction, then the result is much worse than classical machine learning algorithms. In a second example, we look at two-dimensional system. So here we have a 2D anti-ferromagnetic random Heisenberg model where all the interaction Jij is randomized. And basically, the goal of the machine learning model is that given a new set of Jij, predict the ground state. We consider a training data of 100. For each of them, we perform 500 randomized measurements to construct classical shadow. And similar to before, we choose the best ML model from this set. Figure B shows the result from exact values computed from DMRG, as well as ML prediction. So here we are plotting the 2-point correlation function in the ground state. So note that for a two-dimensional system, when one applies DMRG, it actually scales exponentially in the width of the system. So these are basically an exponential time algorithm. On the other hand, the machine learning model is very efficient. So when one goes to a larger system size, actually, even for this 5 by 5 system size, the ML prediction is already much more efficient than the MRG's prediction.
Can I ask a question?
Yeah.
So the non-random Heisenberg model in 2D, it's not known whether there's a gap. Does the randomized model have a gap?
You mean the spectral gap? Yeah, I'm also not entirely sure. I don't think it might not be known. So actually, yeah, so during the theorem, in the theorem that we discussed, we're looking at having the spectral gap. However, for the numerical experiments, we wanted to have something more challenging for the ML model so that we can see that the theorem is of a more, like the theorem as being established, that's already true. So just verifying the theorem doesn't seem that inspiring. So basically here we're looking at settings where we go beyond this, the theorem. So like, for example, we're looking at a phase diagram here. So during the phase boundary, the gap actually closes. Yet we still see that the classical ML model can make good prediction. And similarly for two-dimensional random Heisenberg model, I'm not entirely sure about the gap. It could be true that the gap might become kind of small, but nevertheless, we see that the ML prediction is very accurate. So here we're just showing one examples, but we've actually generated many different Heisenberg model, and we see that the prediction of the ML model is actually pretty good across all these different realization of this random Heisenberg model. So I hope that answers the question. So that concludes the second part of the talk. In the last part of the talk, we're going to look at training machines to classify quantum phases of matter. The task here is also pretty standard. Given a quantum state rho, we would like to predict which quantum phases of matter the state rho is in. So for example, here, the goal is given some classical representation. The classical ML model has to predict whether it's in a trivial phase, in a symmetry-broken phase, in a topological order phase, or in some symmetry-protected topological phase, etc. Again, we're going to utilize the classical shadow technology. We're essentially going to represent the quantum state rho using this two-dimensional array, sigma ti. Particularly, recall that this representation yields a result that's similar, approximately equal to rho when one looks at property. So this approximation is not under, say, trace norm, but under many properties that we wanted to predict. So now in the machine learning setting, we're going to look at a supervised setting. Basically, we're also going to have this training data, which tells us for the given state, what is the corresponding phase. For example, this state corresponds to trivial, this state corresponds to symmetry broken, etc. And now the goal of the classical ML model is that given a new state that's not inside this training data, it wants to make good prediction for the phase of matter. Essentially, what the machine learning model has to do is it has to find a classifying function that allows it to separate the phases of matter. So for example, if there are these different states, A, B, D, H, and C, G, E, F, basically the machine learning model has to find some separating function that allows it to classify between this phase and this phase. So for example, if we look at symmetry-broken phase, there's typically a local observable O such that in one phase is greater than 0, and in the other phase is less than or equal to 0. So in this situation, basically, it means that there exists a very simple linear function, which is a local observable. So when I say linear function, I mean a linear function in the density matrix rho, because this is the mapping from rho to trace of a rho trace of a rho, that's a linear function. So basically, in this kind of simple setting, there exists a linear function to separate it. However, in proposition 2 of our paper, we proved that suppose that we have two distinct topological phases, A and B, then there's actually no linear function, no local or no global observable that exists such that it can be used to separate the two phases. So note that here, this no-goal theorem holds for any observable And it includes observables that act non-trivially on the entire system. For example, this observable could even be some highly non-trivial unitary rotation of the entire system followed by some measurements. Despite that, basically proposition 2 shows that no such observable exists that can be used to classify genuine topological phases. So recall that two states are in the same topological phase if they are connected by a constant depth quantum circuit. Basically, in order to establish this theorem, what we do is we consider random constant depth circuit, like a randomized circuit, and then look at the statistical property to show that this is impossible to happen. So basically what proposition 2 shows is that we actually need a much more powerful machine learning algorithms that can learn nonlinear function, such as trace of O row tensor row, or a more general analytical function, such as f of rho. In order to do so, what we are going to take is we're going to utilize this concept known as kernel methods. Basically, what we're going to do is we're going to learn a linear function in an infinite dimensional space. That is, we're going to map each of the state row to this infinite dimensional vector. So it might look a bit daunting at first, but I will try to go through it step by step. So first of all, in the innermost layer, what we're doing here is we're looking at a subsystem consisting of qubit I1 to qubit IR. And utilizing a classical shadow formalism, we can construct an approximate reduced density matrix for this subsystem based on the randomized measurement outcome. That is, the sigma TIL corresponds to this 2x2 complex matrix for the teeth randomized measurement on qubit IL. When we do this tensor product followed by average, we're going to construct a reduced density matrix. What we're going to do next is we're going to vectorize it. So it now becomes a vector. Then we concatenate all the possible R-body system. So we just look at the vectorization and we just concatenate them. Then we concatenate all sizes of the subsystem. So from subsystem of size 1 to size 2 to size 3, so concatenate all of them. So if we just learn a linear function here, it will only correspond to a linear function in the density matrix. So what we're going to do next is we're going to perform a degree D polynomial expansion. We're going to take this very high dimensional vector, and then we are going to tensor product them with itself. So that basically every entry in this even higher dimensional vector corresponds to some monomials in the reduced density matrix. We then concatenate all degree so that in principle, the machine learning model can learn a general analytical function. So now by learning a linear function for this vector phi shadow of ST of rho, it's equivalent to learning an arbitrary analytical function in the reduced density matrices. So now that's the ML model we're going to consider. Again, we're going to consider these ML models that have essentially infinite capacity. Basically, all it does is it's learning a linear function in this infinite dimensional space, which corresponds to a nonlinear function in the density matrix row. So one might wonder, how do we make that learning efficient? So essentially, using kernel trick, all we need to do is to efficiently compute the inner product. So in particular, the inner product between these two infinite dimensional vector can be organized such that it has this closed form that it's what we call a shadow kernel. Furthermore, computing this shadow kernel only takes a classical computational time that's linear in the system size and quadratic in the number of measurements we take for each state. So what it means is that essentially training this classical machine learning model only takes time polynomial in small system in system size n, number of measurements capital T, and a number of training data capital N. And in practice, it's very efficient. So now, similar to before, after discussing the task, the machine model, we're now going to talk about the theorem. In particular, in the paper, we proved the following. We showed that if there exists a nonlinear function of few body reduced density matrices that can classify phases, then the classical algorithm can learn to classify these phases accurately. Furthermore, the training data size and the computational time both scales polynomial in the system size. Furthermore, what the machine learning model would do is it would actually construct the classifying function explicitly. So by just looking at it, one could get a sense of how to really classify these different phases. And what the theorem tells is that as long as such classifying function exists, the machine learning model is guaranteed to find it. So some examples of classifying function based on few body reduced density metrics include twist operator for classifying 1D Haldane phase from trivial phase, the whole conductivity for systems that's adiabatically connected to free fermion, or topological entanglement entropy in a constant region for classifying topological order. So now what we're going to consider is to see how well does the proposed classical ML algorithm perform in actual physical systems. The first example we're going to look at is a one-dimensional symmetry-protected topological phase. Here, we're going to consider 500 randomized measurements to construct classical shadows for each state. And we're going to utilize an unsupervised version of the machine learning model. So basically, what it does here is that what we consider here is that there's no label training data. We're just being presented with a bunch of different states, and the ML model has to figure out the right clustering for the different phases. In order to do that, we're going to consider a kernel PCA that utilizes this shadow kernel that we just proposed. We're going to look at here we're going to look at bound alternating XXC model, which has a phase diagram that's look like this. By tuning the ratio between J prime and J, as well as delta, one can explore a trivial phase, a symmetry broken phase, and a topological, a symmetry protected topological phase. In figure C, we consider applying the ML algorithm for delta equal to 0.5. There's only two phases in this line. And as one can see, in the representation learned by the unsupervised machine learning model, basically what it does is we're going to map this quantum states, which is a high dimensional object, into this two-dimensional representation that allows us to see how it's being grouped. Particularly, we can see that in this two-dimensional representation, the machine learning model correctly groups all the trivial phase, all the states in the trivial phase, and all the states in a topological phase. Basically, here it's a SPT phase. On the other hand, in this line, delta equal to 3.0, there are three different phases. And similar to in this case, the machine learning model also accurately identifies that there are actually three different phases and group them correctly. And furthermore, one could also look at the structure. For example, these 2 points correspond to states on the boundary of the phase. And one could see that the machine learning model can also recognize which states are actually on the boundary. Like, for example, it has this nice U shape that's shown here. We also observe similar results for a two-dimensional topological order phase. Here we again look at 500 randomized measurements. And for this setting, we're going to look at a collection of states that's being generated by either applying some random constant depth circuit to a torical ground state or applying a random circuit to a product state. So as one could, from physical knowledge, we know that when the steps of the circuit is sufficiently low, then there is a clear signature that these belongs to two different phases. However, as the circuit depth increases, the state that's being generated are no longer in the same phase and could be merged together. And that's essentially what it found by the unsupervised machine learning model. So in figure B, we show in the x-axis the circuit depth over code distance, and the y-axis shows these one-dimensional representation found by the ML model. And as one could see, for small circuit depths, the machine learning model can accurately capture the distinction between the two phases. On the other hand, when the depths start to increase, the phase boundaries start to collapse and the two phases become merged together. In figure C, we show the classification accuracy. That is, we look at when it's being clustered, how well does that perform? We also compare it to some other methods, in particular, convolutional neural network. So here, the green points consider the result for using this shadow kernel, which is an unsupervised method. It doesn't require any label training data. We also compare with a more traditional method known as convolutional neural network, where what it does is it performs a POV measurement on the original quantum state, and then just feed that measurement result into a convolutional neural network. And one could see that the classification accuracy for such method is when we have some circuit depths actually performs not much better than just random guessing. The reason for that is because in this traditional framework where you do POVM followed by a convolutional neural network, despite the nonlinear functions that's implemented inside the convolutional neural network, it actually corresponds to learning a linear function in the density matrix row. And we have proved that it's impossible for any such methods to classify topological order phase, and that's why convolutional neural network doesn't perform very well. However, we can actually feed in convolutional neural network with the classical shadow representation, and then we see that it performs much, much better, and actually slightly better than just shadow alone, because it's an unsupervised method, and also convolution actually have a better structure in understanding some of these local geometry. So now to conclude, in this work, we proved that classical machine learning algorithms informed by data from physical experiments can address some challenging quantum many-body problems. In particular, as a consequence of Theorem 1 and Proposition 1, we rigorously established the advantage of classical machine learning models that can learn from data over classical non-machine learning algorithms in a physically relevant task. So looking forward, there are still many open questions that remains to be answered. In particular, can we establish advantage of ML over non-ML algorithms in more kinds of problems? And can we establish rigorous guarantee for other types of quantum many-body problems using classical or quantum machine learning algorithms? That's it for my talk, and thank you so much for listening.
Thank you so much, Robert, for absolutely beautiful introduction to your new methods. Very interesting, and I'm sure there'll be a great deal of discussion. So I'm going to stop the screen sharing for a moment and see if people want to have a discussion. I hope that people who talk will turn their video on so we can see you and have it face to face. Are there comments? No comments? Well, then maybe I'll ask if you've thought a bit about using quantum machine learning to improve your methods.
Right. You mean at the end?
Well, you mentioned that as an open problem, but are you thinking about it, and have you made any progress?
Yeah, so I do have thought quite deeply about what quantum machines can improve our ability to learn about the physical world. Not quite at the moment, not quite in the context that I've been looking at so far, like classifying quantum phases and predicting ground states. I think they are still powerful, but it's a little bit hard to, at the moment, I think it's still a little bit hard to understand that. However, we have other results that look at the power of quantum machine learning algorithms in learning about physical world. Actually, I think Jordan Kotler has talked a bit about our recent progress on that front in this seminar. It was called the exponential separation between learning with and without quantum memory. So I was also on that project. So there, we look at more basic problems, and then we showed that there is an advantage for those basic questions. However, I would imagine that for classifying phases of matter, quantum computers could also be, or quantum machine learning algorithm should also be useful. But how useful would that be is not entirely clear. I would imagine that there could be some large polynomial advantage, but given these results that I presented so far here, I don't think there is a large exponential advantage for using quantum machine learning algorithm. But I think from a practical point of view, a large polynomial advantage, say much higher than just quadratic, could still be very evident in near term. So at least that's my opinion on that front at the moment.
Great. So does anybody else have some comment or question or like to enter the discussion?
Oh, I have some questions. Oh, hello. Hello. So may I ask a question about the classification result? I remember you mentioned that if there's if R reduced density matrix is enough to do the classification, then there is efficient process.
Yes.
But if R reduced density matrix is enough, so I'm confused how does classical shadow play a role? I mean, it seems that it's also efficient to have full tomography for each R local subsystem.
I see. Okay, so are you asking about the assumption, like how people think about whether this assumption is true, or are you asking about the follow-up question, or are there actually two questions?
Oh, the same question. I'm confused. How does classical shadow play a role here?
Oh,
because
I see.
I thought full tomography seems enough to do this task.
Yeah, so I think I think in that case, classical shadow only provides a polynomial speed up over full tomography.
I see.
So like, for example, if you just do like a naive reduced density metrics for, okay, so it depends on what is the geometry of this reduced density metrics. If I remember correctly, I think for Hall conductivity, this low degree polynomial actually spans across different places of your system. So it's not just like completely localized geometrically, but it could have some more longer range kind of things. And in that regime, I think if you just do classical shadow, then you can get all of that in a more simultaneous fashion. Of course, one could also implement like quantum overlap tomography, which are similar to classical shadow in this regard. But yeah, but I would say like if you just do a naive tomography for the reduced density matrices, then in principle, it would take much longer time. I mean, like a system size longer time than just applying these kind of randomized measurements for reconstructing them. And furthermore, for some nonlinear functions, so that's one. And I think for some nonlinear functions, it's also much more efficient to just do randomized measurement to estimate them rather than doing full tomography followed by estimating these nonlinear function, as we have shown in some of our follow-up works. Like for example, we have this paper with the Innsbruck team, with Peter Zollner's group on this mixed state entanglement detection. So there, basically, we need to estimate a degree 3 polynomial function in order to certify entanglement in mixed state. And there, one could also definitely do like a reduced density metrics, quantum state tomography, and then implement this nonlinear function. But we found that if you just do randomized measurements based on these classical shadow formalism, it's much more efficient. So I would say that's more like it's more like a polynomial advantage rather than a exponential advantage over quantum state tomography. So hope that.
So is a nonlinear function of maybe the density matrix is only up to 3?
Oh no. Oh, are you asking asking for the mixed state entanglement?
Yeah, for example.
Yeah, for that, like mixed state entanglement, that's up to degree 3. But say if you wanted to estimate topological entanglement entropy, that would be different. That could be a much higher degree.
Thanks.
So are there more questions or discussion? Kathleen?
Yeah. So I wonder, how could you train the classical neural network with infinite wise?
Oh, yeah. Basically,
Yeah,
what
you-
happened? Sorry.
You are using the Newton kernel, right?
Yep. So you're wondering like how underlying, how does it work? So basically what happens there is that when you consider such a big neural network, then everything linearized. That is, what it means by that is when the neural network only differs slightly, like you train it by just taking a tiny gradient step, because the neural network is so big, by just taking that tiny gradient step, you actually reach a training error of 0. So basically what happens there is that you can consider a first order Taylor approximation to the neural network. So essentially it becomes like a linear function. Again, it's like a linear function over an infinite dimensional space. And then what one could do is one analyze that infinite dimensional space, and basically that's how neural tangent kernel arises. So it's essentially based on the idea that when you have this huge network, when you just take a tiny step, the training error quickly reaches 0. So you can basically think of the neural network as a linear function over an infinite dimensional space, which now becomes very similar to a kernel method. And that's how one could efficiently train such a huge neural network.
So why do you use the Newton kernel instead of the traditional kernel method?
Oh, yeah. So during our experiments, we actually compare all of them. So we consider both Gaussian kernel method, infinite width neural network, and other kernel methods. Yeah, that's a good question. I guess you're more of asking what kind of benefit do you gain from using these neural network or neural tangent kernel, or like this infinite width neural network. Yeah, so people have also been investigating that. At least in my case, I see that the performance of infinite width neural network and Gaussian kernel method doesn't differ. Okay, so it depends. So here we're only testing infinite width V4 neural network, but essentially similar to how there's all these variety of different neural network, there's also all these variety of neural tangent kernel as well. So you can consider the infinite width version of a convolution neural network, an infinite width version of a graph neural network, etc. And basically by considering all these different methods, they generate different kernel, and different kernel provides different inductive bias, which means that it provides a more natural class of functions that it's good at learning. So I think what people have found so far is that if you consider, say, the infinite width version of convolution neural network, it actually performs better than some of the best kernel that people have cooked up for doing image classification. So I think that's one reason from a practical perspective, is that maybe by considering kernels that's constructed from neural network, it has a more natural or a better inductive bias for the problems that you care about. So that would be one. But I mean, at the end, it's still just another kernel. So I would say it's more like another kind of way for designing kernels, because the kernels that it ended up giving is actually, it looks very weird, but the corresponding neural network is very natural. So I think it's one benefit of it is that it allows you to operate in a more natural regime and producing a kernel that corresponds to that regime. So I would say that that would be one benefit of using infinite width neural network compared to some traditional kernel methods. Like for example, if you use Gaussian kernel, that's just using L2 norm to compute the difference, and then you exponentiate it, right? However, maybe that's not the right way of looking at the geometry of the problem. Maybe it's better to look at some local structure and so on. And yeah, and that's what essentially this infinite width convolutional neural networks actually corresponds to.
And also I saw you you use L2 norm to quantify an error. So the kernel method is more suitable for the L2 norm, right? So, but if you like quantify the error by L1 norm, so what will happen? What kind of method can you use?
Oh, you mean like in order to quantify prediction error,
Yeah.
what if you use L1 norm instead of L2 norm? Yeah, that's a great question. Let's see. I think it doesn't. You're asking in that case, would kernel method be better or something like that?
Because I think the kernel method works very well just for the L2 norm, right? But for the L1 norm, like what kind of method will?
Oh, I see.
Yeah.
Yeah, I'm not entirely sure. That's a good question. It does seem like kernel method work well. But I would imagine that when the L2 norm is good, the L1 norm shouldn't be that different. At least for average prediction error. Of course, they're still not that related because. But I thought you can always upper bound one by the other. Like if you just take the square root of the L2 norm, I mean, of this least square error, then I thought there is some relation with respect to.
Well, by the relation would it be like by some number of like 2 to the power of n?
Oh, but here it's an average, and I thought average has much better scaling. But it's a good question. I'm not entirely sure at the moment.
So I think we could have a very productive discussion between physicists and mathematicians here. Kaifeng is a very good mathematician.
I see.
Maybe
Yeah, I'm not entirely sure at the moment, but I think that's a nice question.
I'm just wondering like how, yeah, I want to know.
I think this is a very interesting question to continue offline.
Yep.
Yeah.
So, Robert, thank you again for a wonderful seminar.
Yep. Thank you so much.